Hey folks, let's get into this thing called the intermediate value theorem. So we have two theorems now. We have the squeeze theorem, which we talked about earlier in this unit about a way to find limits. The intermediate value theorem doesn't find limits for us; it actually finds values, and so Corpy calls it the Y value theorem. He says it shouldn't be called the IVT; it should be called the YVT. Instead of calling it the intermediate value theorem, he calls it the Y value theorem. And in his head, this should be called the YVT because it guarantees Y values. It's a pretty straightforward theorem. So, what are the requirements of this theorem? Let's start off with f is continuous on closed interval a to b. So there's the first requirement. Your function must be continuous on your interval, and your interval has to be a closed interval. So we can't apply the IVT if one of these endpoints are not included. Then blah, 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 takes on all the values, what that means. So what that translates to, what this is saying, okay, is that if you have a continuous function, I'm going to highlight the next part too, and then we'll talk about it. Then we are guaranteed at least one value, one x value, between the endpoints such that f of c equals that number. All right, so the picture over here I think explains it the best. So first of all, is my function continuous from a to b? On the closed interval from a to b, yes, the endpoints are included. The limits as we approach from the one side equal those function values, and we don't have any discontinuities in between, so we have a continuous function. The idea is, if you have f of a is less than f of b. If f of a is less than f of b, then as I travel from f of a to f of b, it's impossible for me to not at some point cross over this value y equals u. It's impossible for me to cross over this height. That is, we know that this y value is between f of a and f of b. It's between these two y values. So it's impossible for me to go from this point to that point without some point crossing this height of u. That's it. That's the intermediate value theorem. So what do we have to prove if we're trying to prove the intermediate value theorem? Well, there's three conditions, similar to what we did when it was continuity. So number one, we must first prove f is continuous. And it's not just continuous, it's continuous on the closed interval a to b. Once we've proven that f is continuous on a to b, we need to prove that one of these y values is less than the y value that we're trying to find, which is less than the other y value. Now, I could have this graph flip-flopped, and f of b could be lower and f of a could be higher if I just did like a horizontal reflection. But the point is that this value falls in between these two values. So I would then prove that f of a is less than f of c, which is less than f of b. Okay, c is some x value in between here, and that function value at c is smaller than one of the endpoints and taller than the other one. So we need to just make this statement. Now, sometimes these can be flipped, like I said, but notice it's not less than or equal to, it's less than. And then the third part is we just do a quick write-up. We do a write-up using the intermediate value theorem in our argument. similar to the way we use the squeeze theorem in our argument. Okay, let's take a look. So this one's kind of just a thought process. There's not really any functions that we would apply to this one. So we measure the outdoor temperature on our back porch to be 47 degrees in the morning at 8:15. Then we measure the temperature again 4 hours later to be 62 degrees. Explain why there must be a time between 8:15 and 12:15 p.m. where the temperature on your back porch on that day had to be 51.351 degrees Fahrenheit. All right, so stop and just like think it through. First of all, it's just like kind of common sense. Like, yeah, if it was 47 and now it's 62, of course it had to be 51.351 at some point. But why? Why? You can't just say, because I said so. We have to make a proof here. So let's set up our conditions again. And that's what the IVT is, our proof for us. So let's set up our conditions. We have to first show that F is continuous. Well, what is F in this case? What is the thing that's changing in this story? There's two things that are changing. Well, hopefully you thought one thing that's changing is temperature. The other thing that's changing is time. My function value or my Y values, would that be the temperature or would that be the time? Hopefully you said temperature. It's the temperature that's changing over time. So my temperature is my Y value, my independent variable, my function values. And time is my X value, the independent variable. All right, so let's set up, we have to prove that the function is continuous. So we have to prove that temperature is continuous. Well, we know that temperature is continuous. We don't have to prove anything. Just like if we said our function was a polynomial, you don't have to prove that. You can just say that a polynomial is continuous. And we know temperature is continuous. You can't go from one temperature to the next without continuously flowing across those degrees. So we would start off by saying, since temperature changes continuously from 8:15 a.m. until 12:15 p.m. All right, so now we've just established what? We've established that temperature is continuous on the time interval, or on the interval. I shouldn't say time interval. In this case, it's a time interval, but it won't always be. We've established that our function is continuous on the interval. And now we need to establish that the temperature that we're talking about fell between the endpoint temperatures. So we would say something like 47 degrees Fahrenheit is less than 51.351 degrees Fahrenheit. Notice all the detail that I'm adding, units. If you have units in the story, you have to have units in your answer, which is less than 62 degrees Fahrenheit, comma. So what have we established? We've now shown that our function is continuous, and we've also shown that the temp at the beginning, so the temp at 8:15 a.m. and the temp at 12:15 p.m., the temperature that we're referencing falls in between those two temperatures. So we've established that we're continuous. We've established that the temperature that we're talking about falls between the endpoint temperatures. And now we do just finish our write-up. Since the temperature is continuous and the temperature falls between the endpoint temperatures, then remember at this point, when we did the squeeze theorem, we'd say by the squeeze theorem. Here we'd say by the IVT, comma, there exists some time between 8:15 a.m. and 12:15 p.m. such that the temperature was 51.351 degrees Fahrenheit, period. Now, when we do an equation, this will be a lot easier. We don't have to do all this extra write-up because we could say like f of x, and we can talk about the interval as being x. So we can, this part actually gets a lot quicker, but this is the basic structure. Prove continuity. Prove that the point that you're talking about falls in between the points that you know. Reference the IVT, and then just say there exists some time such that blah, blah, blah. And you'll see what I'm talking about more with the next example. Okay, based on your two readings, is there a way to determine the exact time the temperature was 51? No, there isn't. You can't say specifically when was the temperature this temperature. You can't say that. You don't know that. But what this thing does, this is what we call an existence theorem. Note. This is an existence theorem. Underline existence and theorem. This is an existence theorem. We cannot determine when it happened, only that it did. I cannot determine when the temperature was 51 degrees. I just know that it at some point was 51 degrees. That's what an existence theorem is. So we know that it had to have happened. We just don't know when. All right, let's take a look. Let's try. Okay, so first Corpy's talking about, let's figure out when can you even apply the IVT. So you can't just automatically say that I'm going to do the intermediate value theorem. We have to first make sure, what are our conditions? We first have to make sure that our function is continuous on the closed interval. So let's take a look. We got this crazy piecewise function, and we're looking at different intervals on which to try to figure out whether or not the IVT can be applied. I'm not trying to figure out what the actual y value is, or even if it happens, I just want to figure out, is there a way to apply, am I allowed to apply the intermediate value theorem? Well, let's try to figure out what's happening from -4 to -2. Well, if I go from -4 to -2, I'm completely within this interval. So I would only use this piece of the piecewise function. And what can you tell me about this function? It's a what? It came over, man. What is it? This is what we call a polynomial. It's over. If I know I have a polynomial, I know I'm continuous. So I would say f is a polynomial on -4 to -2. Notice I did inclusive. So what does that mean? F is a polynomial. That means that f is continuous on that interval. So I can now say IVT can be applied because f is continuous for all x that are an element of -4 to 2. Remember, we're not trying to actually prove the IVT here. We're just trying to prove that we can use the IVT. We're proving that it's legal. All right, let's look at the next one. Okay, now we transfer from -3 to 0. So this gets a little bit tricky because as you go from -3 to 0, you cross over a transition. Now, this is a polynomial. This is a polynomial, so I'm not nervous about the functions themselves. I'm nervous about what happens when you switch from x is less than or equal to -2 to x being greater than -2. So we have to, how would I figure out if these two functions are continuous at x equals -2? Pause and think about it. You should be able to do this. How would I figure out if these two equations are continuous at x equals -2? I would prove that there was a point, and I would prove that the one-sided limits are equal. Proving that there's a point is really easy. When I plug -2 into this, do I get a number? Yes. I don't even care what the number is. I just know that there's a number there. The tougher part is proving continuity from looking at the one-sided limits. So let's look at, actually, I do have to prove it all, don't I? I have to do the one-sided limits and the point because I'm proving continuity. So let's go through. F of -2. F of -2 would get plugged into this equation. -2 times -2 is 4, plus 1 is 5. The limit of f of x as x approaches -2 from the left. So if I'm approaching -2 from the left, it's this again, and I could plug it in again, and I would get 5. The limit of f of x as x approaches 2 from the right equals, now this is where it's going to get tricky. So I plug 2 into this from the right, means I'm using this piece. 2 squared is, oh, we're approaching -2. Sorry, I just wrote 2. We're approaching -2. -2 squared is 4. 4 plus 1 is also 5. Yay! What does that mean? This means that f is continuous at x equals -2, which means the IVT can be applied. IVT can be applied because f is continuous for all x on, where are we going? -3 to 0. All right, let's see if you can try the next one. See if you can try the next one. All right, let's see how you did. So I'm trying to prove continuity from -1 to 1. -1 to 1 actually bumps up into this equation. I don't know if you caught that. So -1 is in this interval, but then it goes to 1, but the 1 is not included here. The 1 is included here. So I still need to check for continuity. So I'm going to run through my continuity check. Let's see. The issue is at 1. At -1, I'm in the interval, and that's a polynomial. So -1 up to 1, everything's good because we've got a polynomial which is always continuous. I need to figure out what's happening at 1. F of 1. F of 1, nope, because that's not included. F of, yes, that's included. 3 times square root of 1 is 3. The limit of f of x as x approaches 1 from the left. I'd plug it into that. 1 squared plus 1, game over. 1 squared plus 1 is 2. And right now, my limit from the left and the point on the right are not equal to each other. Remember that when we talked about earlier in this section about proving continuity on an open interval or a closed interval, that the limit from the left had to equal the point on the right. Now, if you didn't catch that, what you could just do is go on to the next one and find the limit as x approaches 1 from the right. That would be here, and you would get 3, and you'd see that your one-sided limits are not equal. So if you don't remember that thing about the open interval, that's fine. You just got to do one more step. So we would say the IVT cannot be applied because f is not continuous at x equals 1. Next one, we're going from 1.1 to 4.5. All right, so I got to first kind of think about where we're going. Okay, this is 1 not inclusive, so I really don't care about it anymore. 1 to 4.5. Oh, but we do transition. We jump out of this. 1 is included. And I know that the function value and the limit from the right will be the same because it's going to be the same function that I plug it into. So I don't really care that these don't actually meet up. I only care about it from this perspective. But the 4.5 is a transition from here to here. So I do need to do a little bit of work. I need to see what's happening at 4. So let's go through it. I need to prove continuity. F of 4 equals, F of 4 gets plugged into this one. That's 4. 5 minus that's 1. That's 6. The limit of f of x as x approaches 4 from the left. 4 from the left gets plugged into this. Square root of 4 is 2. 3 times 2 is 6. That's off to a good start. The limit of f of x as x approaches 4 from the right. That's just going to be the exact same thing. So that's 6. What does that mean about my function? It means my function is continuous. If my function is continuous, then the IVT can be applied because f is continuous for all x that are an element of this interval 1 to 4.5. Okay, let's take a look. You try that last one. Just think it through. Don't write it out. Just think it through. I think you got tricked because I got tricked when I thought it through. I want the interval to go from 2 to 7. So 2 would be part of this equation, then it would transfer to this equation, and then it'd go to 7 from there. And here's where I got tricked. Because I just proved that their f is continuous at 4, I don't have to worry about that, so I just wrote this up again. That's not going to be true. Because, what does this have? Where does this have a discontinuity? 6 over 5 minus x is discontinuous where? Where? At x equals 5. My function is discontinuous at x equals 5, so the IVT cannot be applied. IVT cannot be applied because f is discontinuous, or you could say not continuous there. F is discontinuous at x equals 5. Okay, so there's a quick review, or not a review, but there's a quick couple of examples talking about when can you apply the IVT and when can you not apply the IVT. So basically, you're just looking for continuity on the interval. So now these are the ones you're going to expect. This to me would be right off of an AP test, free response question, or maybe even a multiple choice, I guess. But there's always going to be, I can guarantee that there's going to be a free response, at least one free response, and at least one multiple choice intermediate value theorem question. There always is. The velocity of a particle. So we've got this particle. It's moving horizontally along the x-axis. So it's just going back and forth like this. Is given by the continuous function v of t. That's a huge, huge hint. What did they just tell us? They just told me that v of t is continuous. So I don't need to prove it. I need to reference it, but I don't need to prove it. Where t is measured in seconds. Oop, there's another warning here, and we're just getting used to this, so I get it if you blazed right by that. But measured in seconds means that we have units. So in our story, when we write it up, we have to make sure that we use units in our story. And v of t is measured in feet per second. Units. You have units. You've got to make sure that you evaluate units. So selected values of v of t are given below. So here's the time. So basically, you've got this story. I know it doesn't really make sense to have a negative. Well, you could have a negative velocity. You just means you're going to the left. This is what happens at time 0. They start the clock. This is the velocity. My velocity was then at 2 seconds was measured, at 5 seconds was measured, and at 8 seconds it was measured. What we want to try to prove between 2 and 5, that at some point the particle was at rest. Well, we got to talk about a couple of things here. We first have to talk about what does it mean for a particle to be at rest in terms of its velocity. What does it mean for a particle to be at rest in terms of its velocity? Well, hopefully you said it means that if the particle is at rest, then the velocity has to be zero. Now, we should say that. It is implied, but I think it's worth it to take the 10 seconds to actually say it. A particle is at rest if its velocity is zero. Okay. We've just made the connection that if v of t is zero, then our particle is at rest. Now we just need to apply the IVT. First of all, is our function continuous from 2 to 5? That's our interval from 2 to 5. Yeah, we know it's continuous because it's from 2 to 5 because it's continuous everywhere. It says it's a continuous function. We still need to reference it though. Since v is a continuous function, notice I do a lot of shorthand because I get sick of writing all this stuff up. Since v is a continuous function for all time t, an element of 2 to 5 seconds. Notice a couple of things now I'm throwing in the mix here. First of all, I'm talking about what t stands for. You have to always say what t is if they give you a story. T is not just some random variable t. In this case, t stands for time. And they gave us units. So at the end of our time interval, we want to say how many seconds there are. So I've established that my function is continuous. Now, I know it's continuous everywhere. But because I'm talking about an interval from 2 to 5, I especially want to focus in on the interval from 2 to 5. And notice I included, even though they didn't include it, I did include it because you have to be continuous on the closed interval. So what's the second part of the IVT? What do we have to prove after we've proven continuity? We need to now prove that this value is between the endpoint values. So I would say, is that true? What value are we looking for, by the way? What are we trying to prove? We're trying to prove that v of t, I'm going to do this in a different color. We're trying to show that v of t is equal to 0 on 2 to 5. That's our goal. Somewhere between 2 and 5, where x is 2 and 5, we want to show that the velocity is 0. Well, what's the velocity at 2? Negative 0.5. What's the velocity at 5? 2. So what has to be true about as I transfer in my y values from negative 0.5 to positive 2, what kind of y values do I have to get? I have to get a y value of 0. So I need to show that this is that sort of lower than this and then greater than this occurs. Since v is a continuous function for all time t, blah, blah, blah. And v of 2, which equals negative 0.5. So I've established that v of 2 is negative 0.5. I'm comparing this to my velocity that I want, which is 0. So that's less than 0, which is also less than the other velocity of 2, which equals my velocity at 5. Since my function is continuous from 2 to 5, and the velocity at 2 is negative and the velocity at 5 is positive, then somewhere I had to hit 0. Now I just need to finish up and reference the IVT. Then, by the IVT, there exists, and now we can use another shorthand, backwards capital E means there exists, some time t that's an element of some time t from where to where, from 2 to 5 seconds, such that v of t equals 0. Which, what does that mean for our particle? that means that somewhere our particle is at rest. Therefore, our particle is at rest. I love these problems. I think they're fun. All right, don't be overwhelmed. It's the first one we've ever seen. Let's look at some more examples. Try to break it down. Show that there is a positive real solution to the equation x to the fifth minus, or x to the fifth equals x plus 2. Well, the first thing I want to do is let me try again. So how would I know where these two graphs are exactly the same height? Well, there's two ways to do it. I could graph them and see where they intersect each other, but we're not allowed to use a calculator, so that move is out. The other option is to set this equation equal to 0, take these two equations and turn them into one equation and see when they, equal a height of 0. Let me show you what I'm talking about. I'm going to take this and I'm going to bump over this stuff towards the x to the fifth. So this now says x to the fifth, subtract x, subtract 2 equals 0. This x to the fifth equals x plus 2 at the exact same places that x to the fifth minus x minus 2 equals 0. I like this format a lot better because now I can say let f of x equal x to the fifth minus x minus 2. Let me write a little note here. Finding the solutions or zeros to f is equivalent to solving x to the fifth equals x plus 2. Exclamation point. If I can prove that this equals 0 somewhere, then I can prove that there is a solution to this equation. All right, so anytime we want to prove that there's just something, that there's just a solution, not what the solution is, just that there is a solution, that's the IVT. We're trying to prove that there's a y value, the YVT. We're trying to prove that there's a y value where this graph equals 0. So let's see, what are the things that we have to figure out? Well, we have to first show continuity. And how do we know that f is continuous? It's really easy. How do we know? Because f is a poly. F is a polynomial. And if f is a polynomial, then f is automatically continuous. What else do I need to know? I need to show that the interval that we're trying to figure out an interval of a positive real number. So if I'm trying to figure out a positive real answer, what are my numbers going to be between? What kind of number? It's going to be some sort of positive numbers. So I'm just going to start to randomly pick a couple different numbers. I'm going to start off with a positive number to plug in. Let's try like 1. What's f of 1? Well, I plug 1 into this. 1 minus 1 is 0. Minus 2 is negative 2. F of 2, let's plug 2 into this. That's 32. Take away 2 is 30. Take away 2 is 28. Why is my math voice happy? Because I'm trying to establish that there's a place where this equation equals 0. And what have I just shown? That the value at 1 is negative 2 and the y value at 2 is 28. So what had to have happened somewhere between 1 and 2? Yeah, it had to have happened somewhere in between there. You had to cross over 0. So we've got enough information now to actually start our proof. Since f is continuous on, okay, what's our interval going to be? Well, if we've shown that at that 1 it's negative 2 and at 2 it's 28, let's just use that as our interval. Since f is continuous on the interval from 1 to 2, Notice I don't have any units, so I don't have to write like time or seconds or anything like that. And now I need to establish that the first one is less than the second one, or is less than 0, which is less than the second one. So f of 1 is equal to negative 2, which is smaller than 0, which is smaller than 28, which is equal to f of 2. I've established that my function is continuous on this interval. I've established that the y value at the beginning of the interval is less than the number that I want, which is less than the y value at the end of the interval. Then I can use the IVT in my argument. Then, by the IVT, there exists some x in what interval? From 1 to 2. There exists some x from 1 to 2 such that f of x equals 0. All right, let's have you, I'm going to try to release you a little bit here. Just do a little bit at a time. Just try to prove the first part of the IVT, which is what? Proving continuity. So I'm going to give you a second. Try to prove that f is continuous. Make an argument. All right, let's see how you did. My argument's going to be very simple. Trying to prove that f is continuous is pretty difficult, but trying to prove that f is continuous based on what it's made of isn't too bad. What do you know about x squared? It's a polynomial. Therefore, it's what? Continuous. What do you know about cosine? Like regular old cosine graph, up and down, up and down, up and down. What is it? It's continuous. So if you take a continuous function and a continuous function and add them together, what do you get? A continuous function. So that's going to be my argument. Since x squared and cosine of pi x are continuous on, now they'll always write it like this. This is an open interval, so you feel like it should be an open interval here. It's not. When to apply the IVT, we have to be continuous on the closed interval. But luckily, these two terms are continuous. These two functions are continuous everywhere. So since x squared and cosine of pi x are continuous on the closed interval from 0 to 2, then f of x equals x squared plus cosine of pi x is continuous on that same interval. Since the pieces are continuous, then the overall function is continuous. Now I need to establish that the number that I'm looking for, 4, is between my y values. So I got to go figure out what these y values are. What's happening to my function f of x when x is 0? Well, let's plug and chug and see what it is. What color? I guess I'll go with light blue. All right, what is f of 0? F of 0 would be 0 squared plus cosine of pi times 0. What's 0 squared? 0. Cosine of 0 times pi, that's 0. So what's cosine of 0? 0 plus 1 ends up being 1. So f of 0 is 1. Now I need to see what f of 2 is. If I was going to predict, what would I hope it would be? I hope f of 2 is what? What kind of number? How big of a number? I hope it's a bigger number than 4, because I want 4 to be in the middle of these two y values. Well, let's see. It's going to be 2 squared plus cosine of pi times 2, which is 4 plus cosine of 2 pi, which is 4 plus cosine of 2 pi. That's all the way around. That's 1 again, which is 5. Good. Life is good here. So now I'm going to take this information and bring it back to my proof. Since f of 0 equals 1, which is less than 4, which is less than 5, which is equal to f of 2, comma, then by the IVT, there exists some x in, oh crap, I did this wrong on this one up here too. I have to go, in my actual argument, I have to go back to the open interval. Dang it. I have to go back, darn it, I made that mistake here too. Look, the proof is talking about the open interval, so we have to talk about this as an open interval. I'm going to leave myself a note for the future. Must be open. This has got to be the open interval from 2 to 5 because that's what the proof is asking us to look at. Sorry about that. So if I go back to this one, I need to change this. This should be an open interval. I use the closed interval in my proof. I use the open interval in my argument. I use this I use this to prove continuity, closed to prove continuity, open to prove the actual proof. I'm going to put that back over here too, for myself more than for you. So sorry if I'm using some of your time here. This should always be closed. So we've established that we've got a closed interval, which means that our IVT can be applied, but the actual number is going to fall somewhere between 0 and 2. So we would say on the open interval from 0 to 2, such that f of x equals 4. So I established that we were continuous by looking at the pieces. I established that the first function value was smaller than the number, which is smaller than the second function value. So then I can apply the IVT on the open interval. All right, last one. The functions f and g are continuous for all real numbers. Boom, that's huge. I'm going to underline it so I don't forget it. Functions f and g are continuous for all real numbers. So they've already established, we don't have to prove it. They've already just told us. We still need to reference it, but they've already told us. The table above gives values of the function as selected values. H is given by h equals f of g of x minus 6. So h is this function where you compose, but when you compose two functions that are continuous, you get more continuous functions. So let's jump right to our proof. Since h is continuous on, or let's write this one up a little differently. Since h is continuous for all x that are elements of, all right, now this is the closed interval because we're trying to prove continuity on the closed interval. So my interval is from 1 to 3, so I want to close that from 1 to 3. And now this is going to be a little bit of work. I have to figure out what is f of g of x minus 6 for my two endpoints. So I'm going to do that over here. I just need to show that I did it somewhere. You don't have to actually reference it in your argument. I mean, you have to reference it, I'm sorry, but you don't have to show your work over here. So what is h of 1? Well, that would be f of g of 1 minus 6, which would be f of, okay, g of 1. Remember how this works? I go to g, I go to 1, I get 2. Now, when I get out 2, I go to y, that gives me a 9. 9 minus 6 ends up being 3. So h of 1 ends up being 3. H of 3 would be f of g of 3. And you don't have to show your work here. If you can do this in your head, g of 3 is 4, then that becomes my new 4, which is negative 1. Negative 1 minus 6 is negative 7. You can do that. But you should show at least how you're calculating h of 3. G of 3 would be 4, so that would be f of 4. F of 4 would be negative 1. Negative 1 minus 6 is negative 7. So is h of r equal negative 5? Going to fall between 3 and negative 7? Yep, we're in good shape. So I now would say h of 1, which is equal to 3, which is less than, no, sneaky, huh? 3 is not less than negative 5, so this time I'm going to flip them around. Greater than negative 5, which is greater than negative 7, which is equal to h of 3. Now, if you don't like doing it that way, you can just write it in the other order if you want to. So in parentheses underneath here, I'll write it the other direction. If you wanted to write it h of 3 equals negative 7, which is less than negative 5, which is less than 3, which equals h of 1, that's fine. You'd still get full credit for that. They don't care what order it is. All you're trying to do is establish that negative 5 is between these two values. Okay, we've established that. Game over. Then, by the IVT, there exists some, now be careful here. I don't know if they'd take a point off for this or not. If they did, I think that's cheap. There exists some, what value are we looking for? We're not looking for an x value. They changed x into r. So we would say there exists some r that's in the open interval from 1 to 3 such that h of r equals negative 5. So that's the end of the official notes there. I think the back of this is kind of nice to look at, though. This is how they would grade. This is what they would need to show. They would be looking for, this would be a 2-point free response question. This is the one right here. This would be worth 2 points. You would get 1 point for showing your work on h of 1 and h of 3. You don't really need to show your work. You just need to show what they are. You could write just h of 1 equals 3 if you did it all in your head, and h of 3 equals negative 7 if you did it all in your head. But you get 1 point for showing that work, and then 1 point for the write-up at the end. Notice, if you write it up without saying IVT, you're out. And then I think this is also interesting to look at. Corpy put on here the 2007, there's 6 free response questions worth 9 points each. This was the average number of points that people got out of the 9 points. So out of the 9 points, on average, people only got 4 and then 3 and then point. That number 3 must have been brutal that year. But the idea that you got to wrap your head around is that you're not going to get 100% on everything. Nobody could get 100% on everything. What you want to do is you want to establish and get at least as many points, like the gist of every problem. You want to get sort of the idea of it and then apply what you know from there. Okay, you got some homework now, and ask some questions in class.